All right, looks like we're right on the hour, so I'd like to welcome everybody to the webinar. I'm going to say good morning to you guys out here from Tualatin, Oregon, where I'm at on the West Coast. I imagine, though, most of you guys are probably joining us from somewhere else in the country or in the world, so if that's the case, good afternoon or good evening. Today's webinar, Cleaner Joints, Stronger Seals, Laser Welding of Automotive Lighting. Modern automotive lighting is as much dictated by its design as it is its functionality. And in the past, automotive lighting really only served a practical purpose, illumination. But today the game's changed. Exterior lighting has become a focal point of car designs, and compromising large, curvy, free-form designs purely for function just isn't an option any longer. With traditional methods, traditional assembly and welding methods, engineers and designers are in a constant battle of limitations, though. But laser plastic welding aims to change all that, and that's what we're going to talk about today. My name is Josh Brown. I'm a market development representative with LPKF Laser and Electronics. Throughout the presentation, I encourage you guys to ask any questions that you have. It helps kind of keep the flow of the presentation strong, also helps us understand what you guys would like to get out of this presentation. If I can't answer the questions as they come in, we'll spend some time at the end in a Q&A, and then if any of those questions are too technical, then I'll follow up with you after the webinar. So before we jump into the technical details, I just want to give you a quick example. If you're unfamiliar with laser welding, then you may not know that it is in production currently. It's a viable welding assembly method for car lighting. And so here's an example. This is a taillight for a luxury sedan. It was a joint project between LPKF and SL Corp in South Korea. And this project had some demanding requirements, and that's why laser plastic welding was chosen. The requirements were excellent aesthetic appeal, they wanted high weld seam quality, and they wanted the joint to be virtually right to the edge of the taillight, and for that reason they didn't want to have to hide the joint. They also wanted low reject rates, and they wanted to do all that without sacrificing durability or cycle time. So they're kind of asking a lot here, but laser plastic welding was able to deliver in this instance. Here's a testimonial from Sim Young Sung, who's the manager at SL Corp. Thanks to the hybrid welding technique, SL Corp has not only produced welding seams of previously unheard of quality, it also dramatically reduced the reject rate. I just wanted to lead off with this because it's good to understand that laser plastic welding is this isn't a pie in the sky thing. We're really talking about true applications that have been put into production, and you can even see them on cars today. So that being said, let's move into the more technical side of the presentation. So here's the topics we're going to cover today. First off, we'll talk about how it works, just so you can get a basic overview of what laser plastic welding is and the concepts behind it. Then we'll talk about an overview of the system. I like to start with the system because it kind of helps you wrap your head around, again, how laser plastic welding is working specifically for automotive lighting. And then we'll talk about hybrid laser welding. It's a slight variation of regular, so to say, laser welding, and it's definitely very important to what we're going to talk about today, and so I want to cover that in detail. And then we'll talk about a comparison of all the methods, ultrasonic, vibration, hot plate, and that'll probably be where we'll spend the bulk of the time for today's webinar. Before I move on, though, I'm going to launch a poll really quick. So what is your primary assembly method? You should see that poll pop up. You'll be able to click on a response and answer it. We'll spend about probably 20 seconds on this, see if we can get everyone to chime in on this, just so we can get a good idea of what assembly methods we're using right now. If you don't have an assembly method, feel free to just click other or leave it alone. About 10 more seconds, then I'll close it out and show the results. All right, I'm going to go ahead and close the poll. Apologize if you didn't have a chance to answer. And I'm going to share that really quickly just so everyone can see it. So 33% ultrasonic, 67% other. I didn't post laser on here. Maybe I should have, but we do have a relatively small data set we're working off of here. But I imagine typically vibration and hot plate would be seen more on there as well. But that's definitely an interesting pull. So I'm going to go ahead and hide that. We'll move on here. All right, so first off, let's talk about how it works. So to do that, I have a quick video here. The basics of laser plastic welding: we have a upper transmissive layer, a lower absorbing layer. The laser is going to pass through this upper transmissive layer, and as it strikes the absorbing lower layer, that laser light energy is turned into thermal energy, and then the thermal energy is conducted through to the upper layer, fusing both layers as they melt together. So in order for laser plastic welding to work, you have to have four main factors. I call these the big four. As I mentioned on the previous slide, you need a transmissive upper part, an absorbing lower part. When I say transmissive, we're talking about transmissive to laser energy in the infrared spectrum. So laser beams with wavelengths of 808 or 980 nanometers are typical. Technically, this layer doesn't have to be transmissive to the naked eye. It just needs to be transmissive to the laser light. So it is possible to weld parts that are opaque looking, but as long as the laser can pass through them. As far as the absorbing lower part, most thermoplastics are transparent to laser radiation in these wavelengths, but by adding soots, dyes, or pigmentations, it's very easy to achieve absorption. Material compatibility, we'll talk about this in a later section, but just know that the materials have to be of similar chemical properties, mostly melting temperatures and a few other factors, to be able to be welded together. I can say, though, if you're able to weld these with other traditional welding methods, then laser plastic welding is capable of welding any of the same material combinations and even then some. And then clamping force. It's important that both pieces of plastic are in pretty intimate contact with each other. Remember, the energy that's created by being absorbed in the lower layer has to be conducted to the upper layer. And in order to do that, intimate contact is required. And to ensure that intimate contact, clamp force is used. So before I go into taillights really quickly, I just want to show you, here's a slide of some typical applications that you'll see laser plastic welding in. A lot of these devices are much smaller than car taillights, and the reason I wanted to bring this up is because as we move to this next slide, you can kind of see the evolution of laser plastic welding, moving from the small plastic sensor housings and consumer products and small medical devices into these large free-form shapes that are taillights. And so we went from a system where you have the optics and the laser delivery system all enclosed in this shroud, kind of a standalone system. And then all those were essentially ripped out and placed on the end of a robotic arm. And in this way we can move and maneuver the laser into any part of the joint of larger parts that we need, specifically taillights. The twin weld system that you see here isn't used strictly for taillights, but it was designed with taillight welding in mind. It's a 6-axis robot, and this allows for, like I said, joining of large and complex curves. It can move in just about any direction it needs to move. It can maneuver and enter the laser into even the most difficult and complex joint designs. Here's another view of the system. From the outside, you can see it's enclosed in a laser class 1 metal shroud, and there's a rotary table here for quick loading and unloading. Here's the same system showing the even further back with the PCU and control unit here. And then one more shot inside. You can see the operator setting up the process. All right, so that's kind of a quick overview of the system. Let's talk about hybrid welding. And before I can jump into hybrid welding, let's start more with regular laser plastic welding. So there's a few different types of laser plastic welding. Let's start in the top left. First off is contour, and this is essentially what I explained in the first slide and what you saw in that animation. It's where the laser is basically making a single pass. Sometimes it can be robot assisted, but in our case, we're essentially doing contour welding. I'll get to the hybrid process here in a minute. The pros of this are it's very flexible. You can do large and 3D parts such as car taillights. The cons, it's slightly slower compared to simultaneous and quasi-simultaneous. Quasi-simultaneous welding in the upper right-hand corner, that's where the laser is going to make multiple passes. The laser beam is guided by very precise and very fast galvo-scanning mirrors. And so you're essentially going to trace the entire pattern of the beam over and over again very, very quickly. Simultaneous welding is where the lasers are going to be formed using fibers or other beam shaping devices to form and pattern the laser to essentially flash the entire joint simultaneously. The pros of this are it's very fast. Cons, it can be very expensive because you have to have dedicated tooling for every individual application and pattern. So that brings us to hybrid welding. Hybrid welding is essentially contour welding, like you saw on the animation that I showed you earlier. The difference is that hybrid welding, besides just having laser energy, it's also assisted by a high-powered halogen lamp. And so we'll talk about this in a little bit, but it's going to improve your cycle time, joint quality, and it's going to soften and anneal the plastic. So here's a cross-section of the hybrid welding head. Essentially what's happening here is you can see the high-powered halogen lamp, and this is a polychromatic light source. And so as I mentioned earlier, the laser, being monochromatic, is going to pass directly through this upper transmissive layer, and it's going to absorb all of its heat into the lower layer. So the only way that the upper layer is going to be able to get heat from the laser energy is through conduction between the two pieces of plastic. Now this is great, and it works for most laser plastic welding applications, and it will work for taillights. But by adding the halogen radiation, the polychromatic radiation, we're able to volumetrically heat the upper layer as well. And so what this is going to do is we're essentially preheating the plastic. We're creating a larger welding zone outside of just the laser. So you can see here, here's the difference between regular, this is conventional contour welding, and then hybrid welding. This white line in the middle is the interface between the two parts. And so you can see the amount of added heating in the upper layer here. This is important for a couple of reasons, and we'll definitely get into these as we go on and talk about the advantages of it, but by increasing this heat, we can do things like speed the laser up. We're going to reduce stress in the part compared to regular conventional welding or other welding methods. And as you can see here, hybrid is faster at 50 millimeters per second, 30 millimeters per second. So let me show you, this will also help kind of wrap your head around seeing the system in action. Launch that video really quickly. All right, so this is the process of laser welding with the robotic assisted halogen source. You'll get to see the cross section here in action. So see, the halogen light will light up, and that's essentially preheating the plastic. It's a larger heat affected zone than what you get with just the laser. Where the polychromatic light is volumetrically heating the upper part. So you can see the slightly larger heat affected zone than the laser. The roller arm here, that's where we're applying the clamping. And then you get a nice, clean, consistent weld. All right, so jumping back into where we were, hybrid versus regular contour welding. Like I mentioned, you can get higher travel speeds. So 80 millimeters per second compared to 50 millimeters per second, because we're essentially preheating the plastic. The higher laser power can be realized because the upper layer is being heated by this halogen lamp. So without the halogen radiation, if you turned up the laser energy, then the housing will essentially burn before the lens is going to even melt or have a chance to heat up. But because we're preheating the upper lens, then we can turn the laser power up and travel the laser faster because the lens will already be heated to the point where we can give ourselves more process room, more flexibility with that, and we're not going to burn the housing doing that. Also, the annealing time is reduced compared to regular contour welding. Essentially what I mean here is, if you're familiar with car taillights, stress added from the welding process has to be removed at the end of the welding process. So whether it's thermal or mechanical, that stress is going to cause potential joint failure later on, and an annealing process has to be done. So essentially the lights are baked in an oven for a certain amount of time depending on the way they were welded. But because the halogen radiation is softening the plastic, then that annealing process is taking place during the weld. So a lot of that can be reduced, and in some cases it's not even necessary after the weld takes place. Also, there's less stress compared to contour welding as far as thermal stress. Like I mentioned earlier, because of the volumetric heating, we're not shocking the plastic quite as much. The laser isn't hitting cold plastic, it's essentially heating preheated plastic, and because of that you're not going to get that thermal load and that thermal shock. Better gap bridging, again, the halogen radiation, the polychromatic halogen radiation is softening that plastic and allowing us to bridge the gap easier because that plastic is going to form into the housing. And then higher process flexibility. Like I mentioned, kind of all comes back to the halogen radiation preheating the lens, and that gives you a lot of extra process flexibility. Here's an example of tensile strength to weld speed. So as you can see, we have conventional contour welding over here, and then the pink line is hybrid welding. And if you speed up your scan speed with contour welding, you can see a very quick drop in tensile strength, whereas it tends to even out and stays very high with hybrid welding. Also, I want to note that this was done at very low laser powers, so we can actually turn up the laser power and achieve higher weld speeds. So as you can see here, this is 40 millimeters per second, about 60 millimeters per second, but in typical production environments, the laser will be traveling at about 80 millimeters per second. And that equates to about 30-second cycle times, maybe less depending on the size of the taillight. I want to make one other quick differentiation. Hybrid and simultaneous welding. Simultaneous welding can be used for welding car taillights. I'm not going to go into it and cover it in too much detail today, but hybrid contour welding, like we're spending most of the time on today, in comparison is flexible. We'll talk about this later, but there's no dedicated upper die, so it's a very easy changeover. Remember, with simultaneous welding, you're essentially flashing the entire joint using a multitude of fibers. So you're feeding multiple laser sources into the joint using different fibers patterned into an array around that joint. And because you're doing that, every piece of tooling with simultaneous welding is dedicated to that specific application. If you want to switch applications, then you have to switch your tooling out, and it can get very expensive. Also comparatively low stress, like I mentioned, the annealing and the weld times. Simultaneous welding does have a very big advantage with cycle times, and this is actually incorrect, excuse me. So this is simultaneous for welding smaller parts. Simultaneous for welding tail lamps, etc., larger parts. There's going to be more heat involved, so the process will be longer than this, closer to 20 seconds. But it is very fast comparatively. But it does require annealing, and the multiple laser sources are very, very expensive, and they tend to burn out quickly, so it requires a lot of maintenance. Talking about materials really quick, Laser plastic welding can weld virtually any materials that can be welded by other methods, and then some. So with tail lamps, ABS, PMMA, PCABS, and ASA are the typical ones. Headlamps, I'm bringing this up because headlamps are not typically weldable. PP to PC just doesn't work. The reason for this is because there's a few factors that go into the weldability of two different plastics. One is the melting range. PP to PC, they tend to have a similar melting range, but the other three factors they don't tend to match up on so well, which are the heat extension coefficient between the two plastics is too high, and then also the surface energy varies too much. These two plastics just don't like to be welded together. However, most headlamps are polycarbonate lenses to polypropylene housings, and so most of the time these are glued. However, with laser welding this can be done. Slight stipulation here, it's not exactly a true PP, it's a PP or PA blend. I can't go into too much detail about it because it's proprietary, but this can be done with laser welding. This is a huge advancement for headlamp assembly because we all know that adhesive bonding of headlamps can be time consuming and it doesn't allow for a lot of flexibility. So the fact that this is there's a potential here for welding headlamps is definitely a big innovation. So we do have a welding material compatibility chart for laser plastic welding. Looks something like this. I've highlighted the main ones here in red for automotive lighting. Notice the PC to PP, it is green, but should have put an asterisk on that. Remember, as I said, it's a PP blend. All right, so that kind of wraps up that part of the webinar. Now let's move into the comparison. So don't worry about memorizing this chart. These are just the factors that we're going to cover in our comparison. And this will just kind of give you a broad overview of what we're dealing with before we get into it. So we're going to cover factors, the durability of the joint, aesthetic appeal, cycle times, process control, part sizes, stress, complex curves, and then we'll get into the equipment and tooling costs. And we've already talked about the ability to weld headlamps and tail lamps. Before we do that, though, let me pull up one more poll. So I'm going to go ahead and launch this one really quickly. What is your major assembly or design concern today? If there's one obstacle that you could overcome, whether you're designing or an assembly, what would it be today? If laser could fix one of these, what would that be? So we'll spend about 10 more seconds on this one. Last few votes coming in. All right, I'm going to go ahead and close this. Apologize if you didn't get a vote. And then share it really quickly. So across the board, it's cost per part or design freedom. Those are the two big ones. And that's typically what we hear a lot is cost is very important when talking about car taillights, typically because they're such high volume applications. And we'll talk about costs, like I said, at the very end. So we'll cover those as well as design freedom. So first off, laser plastic welding provides a very durable hermetic seal. And this is really important when you're talking about taillights. You don't want rejects. We've all seen those fogged up taillights after the joint fails and they get condensation inside of them. This is definitely a big issue. Something that from the engineers that I've talked to that's typically on the top of their list. Laser plastic welding has the ability to produce 90% strength. And when I say 90% strength, I'm talking about strength compared to the parent material. So it's even above friction in ultrasonic welding. The only one that's slightly stronger is hot plate can get stronger. It can get close to 100%. So laser welding does produce very strong, durable joints. Also, I should note that the stress reduction from the halogen radiation will alleviate a lot of the stress that can tend to cause joint failure over time. Complex curves. Laser hot plate and gluing have the ability to weld complex curves. So double curves. We've all seen wraparound taillights. They're getting much more common. Taillights are getting bigger. And all of these are coming with more complexity in the shapes. You're going to run into issues with vibration welding. Vibration is a very popular welding method, and it can weld a reasonable amount of curvature, but the design has to have an axis or a crease in it. So it has to have essentially a linear weld line for it, because vibration welding is essentially moving the parts relative to each other in a straight line, and so you have to have that crease. So double and complex curves are not possible. I didn't put ultrasonic on here. I probably should have mentioned it. Ultrasonic does have the ability to weld somewhat complex curves, but it gets really limited by size very quickly. So typically with taillights and headlights, you're going to struggle to use ultrasonic with anything that does require large curves anyways. This isn't a comparison. This is specific to laser welding. But I did want to mention we do get questions a lot about steps and flanges, and so I wanted to kind of cover this before we move on. But the roller arm does run into some issues. So say you have a step like this, then oftentimes we'll try to either flatten that out, or we can work around it with ways like dynamic clamp tooling, where typically the clamping is applied through the roller arm, but if needs be, we can have the clamping applied with dynamic clamp tooling that is essentially built into the nest. Also, you see joints like this. We typically try to smooth out the inner curve of the joint. So where you see the red line here, instead we'll suggest that you do a more radiused interface between the two parts. And in this way, we're going to ensure that we're going to distribute the clamp force evenly. So as that roller arm travels along here and then hits this step, we can ensure that all of the clamp force throughout that whole process is going to be distributed evenly throughout this entire interface, and you're not going to see gaps being created with different angles of pressure. Back into our comparisons, stress plays kind of into durability like I mentioned on the first slide. Laser has precisely controlled thermal energy, so the heat affected zone is very small. And when you start to weld with mechanical methods, ultrasonic and vibration, and even hot plate, you tend to get a larger heat affected zone. So you're going to be adding a lot of undue thermal stress to the parts, and in some case mechanical stress, and again that can cause durability and joint failure over time. So here's a comparison of laser hybrid versus hot plate on the top. You can see this is a zoomed in view of the joint. You can see a nice clean joint here with laser hybrid welding. And then as we move into hot plate, you can see that it's this inhomogeneous structure. It's a lot of melt blowout occurs with hot plate welding and stringing. We've all seen the stringing happen, and so it leaves inconsistent joints. That's what I'm trying to get at. And then again on the bottom, nice clean joint with laser hybrid welding, and then vibration, you get this scaling effect. A lot of particulates involved with vibration welding. Which kind of brings me to this point, is clean joints. So clean, consistent weld seams are very important. Flash is always an issue when you're welding taillights, and a lot of times it has to be covered up. So we've all seen the two-shot molds, or the coverings on the outside that have to cover up the joints, and these are all limiting you in the way that you can design your taillights. With the ability to put the seam flush to the edge of the light, though, this gives you a lot more flexibility as a designer and an engineer. So we've all seen divided tail lamps where you have part of the tail lamp on the trunk or the door or the body, and they split, say, as the trunk opens. Well, the closer you can get your joint flush with the edge, then the more room you have for illuminated area on that light. And so in some cases it's purely for aesthetic reasons, you can have more illumination on the light, but there's even certain cases where cars are required to have a certain amount of illumination. And so by being able to push your joints out further and not having to hide them behind behind other parts of the taillight that are not illuminated, then you give yourself a lot more design flexibility in this way. Ultrasonic and vibration, they provide relatively clean joints, but you do see more melt flash than you'll see with laser welding. Hot plate, you're going to see a lot of melt flash and blowout, and stringing is the most common issue we hear about with hot plate. So, process monitoring, this is always really important as you talk about production level assembly. So each one of these methods do tend to have good process control, so I really just wanted to bring up laser welding's ability to monitor its processes. Essentially what you're looking at here is a reflection diagnosis system, and what's happening is the test radiation is being applied. So this isn't the same as the laser. It's being applied at a specific angle, and then as you can see here, when there's no gap, you're only going to get one angle of reflection. And so the system will monitor this reflection, and that's going to feed back and say that this is going to be a good clean joint here because there's no gap. However, if there's a gap, which remember we want to avoid because we need that conduction to occur to get a nice clean weld, then there's going to be two angles here. And so the system will monitor that, send it feedback, and at this point the laser could actually in real time slow itself down and heat this up a little bit more, hopefully bridge that gap. So scrap and rejects, again, laser precisely controlled thermal energy. Hybrid welding is going to reduce a lot of the shock and the stress, and then with the matched up with all that in the process monitoring and the fact that you have clean joints, so you're not going to get the stringing or the marring on the surfaces that you get from the mechanical methods. Laser has a very low scrap and reject rate. We've had customers mention that they've had 0% reject rates for over 9 months. So it's the fact that laser is very efficient in this way is a huge advantage for it. Again, the big ones we see with ultrasonic and vibration are the marring and the blemishes from the tools, and then hot plate again is the stringing. So let's move into costs. This is always the one hang-up that most people get to with laser plastic welding. It's definitely the biggest hesitation, and so I want to bring it up here so you can get a good comparison of what you're looking at of laser compared to hot plate and vibration, the two most common welding methods. So again, the biggest hesitation for laser welding system investment is the initial system cost, and so you can see it is more, $350,000 on average compared to the mid $100,000s for hot plate and vibration. So that's definitely one big hang-up. Laser simultaneous, I don't have specific details over here, so that's why I just tended to put these markers instead. So we'll do a slightly different comparison over here, but laser simultaneous welding, including the tooling, you're looking at about $800,000. So these systems get very expensive. Tooling costs, a lot of factors go into tooling. So $27,000 for laser welding, hot plate is about $60,000, and then $46,000. And then again, as I mentioned with simultaneous welding, all of that's very dedicated tooling with many fiber-fed laser sources, and it's extremely complex tooling with laser simultaneous, so it gets very expensive. Quick breakdown of that, I'll come back to that slide. The reason tooling is so cheap for laser welding is because it only requires a bottom nest. There's no top part to this. All of the clamping pressure is applied via this roller arm. Vibration, and actually this should be it's slightly more expensive than laser welding, but it's definitely not bad. Hot plate, because it's a three-piece system, full free-form machine tools, they do tend to get very expensive, and they require tons of maintenance and frequent resurfacing so you don't get the stringing effects that we were talking about earlier. And then again, the laser simultaneous. I wish I could show you a picture of this. I don't have any pictures that I'm able to show you, but the whole entire upper nest is being fed with fiber lasers, and it just gets extremely complex, and you can see that there's just a lot of room for breakdown and maintenance to occur with that. So let me go back to this slide. So then what we did is we broke this down. We took the system investment, the tooling costs, and then its ability with cycle time, availability to get your capacity per year. And then in doing that, this example is amortized over 8 years, with the tooling amortized over 3 years. You get a cost per part of 29 for laser, 41 for hot plate, and 18 for vibration. And again, I don't have a specific answer for laser simultaneous, but it's going to tend to be very high because you have a lot of downtime and a very expensive system investment. So if laser was the norm at 100%, then hot plate welding, even though the machine is cheaper, with the tooling and the fact that its capacity is much lower, you're actually looking at a more expensive total cost of ownership. And vibration is still slightly lower. Vibration is a very economical method. That's why it's so popular. But laser is still very competitive and affordable. So why would you choose laser over vibration? Well, it just really boils down to those advantages that I mentioned in the past slides. Laser provides a really extremely flexible and affordable alternative to traditional welding methods. And it's really kind of the front line of technological innovation for tail lamp and headlamp assembly. So some disadvantages. So tight part tolerances, mostly I'm talking about gaps here. Gaps should really be no more than about 0.2 millimeters. Now this is after clamping is applied, so it's not just the two pieces resting on each other naturally. Once clamping pressure is applied to the part, you shouldn't have more than 0.2 millimeters of a gap. We can overcome 0.2 to 0.4 sometimes, but we like to see no more than 0.2. It just makes your process that much easier. Different and new joint designs. I didn't want to say difficult joint design because it's not. It's actually a very simple joint design. Compared to other welding methods, laser plastic welding doesn't require multiple weld ribs, so you don't have to have a weld rib or weld leg on the lens and the housing. It only requires that on the housing. So the lens can actually be a flat piece, flat surface. And because of that, the joint's actually simpler. It's cheaper to design because you don't have to have multiple slides in the injection molding process. However, it is different and it's new, so you're going to have to adapt your part designs to it and change for laser welding specifically. Which kind of brings me into the next point, the learning curve and the maturing of the weld process within your organization. If you were to adopt laser welding, there's definitely going to be some training and some things to figure out before you can be fully proficient in it. So definitely something to take into consideration. Steep steps and flanges, as I mentioned, they can be difficult sometimes to clamp, but not impossible. We can get very creative with our clamp tooling, but they do add some difficulty. And then the initial capital investment. So as I mentioned, the total cost of ownership over time and your individual part costs are going to be lower, but the initial capital investment is going to be higher, and this can definitely thwart adoption sometimes. So just to recap, laser plastic welding provides strong durable joints, quick cycle times, the ability to weld complex shapes with very low stress, both thermal and mechanical stress, clean the joints that can be flushed to the edge, excellent process monitoring, which equals low reject rates. There's also low tooling and production costs. The annealing time was a big time saver there, and gap bridging and further stress reduction. So that being said, we can jump into the Q&A now. If you guys have any questions for me, go ahead and enter them in the questions box. I'd be more than happy to answer them at this time. If not, then feel free to take down my contact information. If you happen to have any questions after the webinar, then you can send them to me. We can take care of them then. We also have a design guidelines document specifically tailored for automotive lighting. So if you're curious to know more about how you would go about designing your taillight or headlight for laser plastic welding, then go ahead and send me an email and I can get that to you as well. I got one question so far from Carlos. It says, what about maintenance costs? Carlos, laser is excellent for maintenance costs. There's very little downtime. I don't have a specific figure for maintenance costs, but availability is what I was talking about here with very little downtime. So your downtime is going to be about 5% compared to where you have higher maintenance costs with, say, hot plate or vibration, or very high with laser simultaneous. So I don't have a hard cost factor for you, but compared to these other methods, your maintenance costs are going to be lower. The laser themselves tend to run for tens of thousands of hours. We don't like to throw out a exact quote, but it can be between 10,000 and 20,000 hours for a laser source before they start to really require any maintenance on them. Other than that, the machines are designed to run 24/7, 365. So I'll go ahead and hang on the line here for another minute or two. If you guys have any questions, again, go ahead and enter them into the webinar interface. If not, then we can kind of conclude the webinar at this point. So I'd like to thank everyone for coming. I appreciate your time, and I look forward to corresponding with you guys further on any questions you may have about laser plastic welding and automotive lighting.